Okay, hello. Today we are going to be talking about our extra credit Algodoo project. My name is Arjan,
I'm Shreya.
I'm Nick.
and today we'll be focusing on the concepts of collisions, specifically on conservation of momentum and how that relates to energy. So we'll throw it over to Nick to start us off.
So the goal of this simulation was, as Arjun said, to demonstrate the concept of momentum and energy, conservation of those things, and also elasticity and collisions. So a collision is just a short interaction between objects like this, and momentum will always be conserved with a collision between these two objects, unless there's an external force in the system. So momentum is the product of mass and velocity, and as I just said, it will be conserved. And energy also plays a part too. Energy, specifically kinetic energy, is 1/2 mv squared. And energy can be conserved, but sometimes it's not. So when I mean conserved is that if you calculate the momentum of both objects, they should be the same before and after the collision. In the simulation, we're going to be demonstrating two different types of collisions, elastic and inelastic collisions. Inelastic collisions is when objects will stick together once they collide, and that's when energy is not conserved. And elastic collisions where objects will bounce off, and that's when energy is conserved. So as we run the simulation, we will see how that is demonstrated. So we will throw it to Arjun, who will describe the actual simulation.
Yeah, so just showing off some of the things that we built in Algodoo. This is what our overall game looks like. So this is a game after all. So the rules of this game is what we're going to be doing is taking this white sphere over here, which has a central thruster attached to it that we can toggle using the I key. We'll use that to kind of get it through the track and hit the yellow sphere into the green box over here. We're trying to hit it with enough incoming velocity to push it into the green box, but not so far or not enough to land in any of the red boxes. So some key things to note before we get started is the material to make the actual track itself was the default material. As you can see here, just some noting one of the more important parts of the track itself is that all of the track has this friction value of 0.5. So do the spheres themselves. So shows that we are taking into account kinetic friction while we're running this model. You can see gravity is on, and air friction is technically on, but throughout this model, we're actually going to run it with 0. So it's off, no air resistance, gravity on, but kinetic friction is being taken into account. Then we can look at each individual ball. So we can see from their material calculations is that, yes, they both have friction. One of them is going to be 1.5657 kilograms, and it has a restitution of 1. We'll get into that a little bit more later. And the other one has a higher mass, which of 3.0 kilograms, which comes into play when we talk about our specific model, has that friction as well, like everything else in this model. So kinetic friction is being modeled. And it also has a coefficient of restitution of 1.00. So the coefficient of restitution is the velocity after the or before the collision divided by the velocity after the collision. So a coefficient of 1.00 ensures that there is no velocity lost in the specific collision, ensuring conservation of momentum. So before we quickly get to the actual model, I will kind of just show how this model is going, or how the simulation is going to work. So we started off, get the ball going using that I key, get it going up the track, and then it's going to hit the other ball. That'll go, and then hopefully we'll try and get it to land in the green or the green place here, which we did. So that round's a success. Before we head it over to Shreya to talk about the specific model, I'm just going to also demonstrate what it looks like when we turn the restitution values down. So I'm going to turn the restitution down, let's say to 0.3, a much lower value. So it's going to be much less of an elastic collision as a result. I'm going to change this one also to 0.3, and we're going to see what happens. So a big thing to note is that the reason why this model of, and specifically the restitution of 1, allows for us to get the ball going with a large velocity is because initially we're starting out with all the velocity going to the right. So I'll indicate that here. So as you can see, all the initial momentum is going to the right. When we have an elastic collision, that allows for a lot of velocity going to the right in the final yellow sphere because the white sphere, collides off of it and goes left. And to ensure conservation of momentum, that means the yellow sphere has to go with a higher velocity to the right, which allows it to travel farther and hopefully get into that green box. When we make it an inelastic collision, they tend to stick together and both of their final velocities point to the right, which actually causes the yellow sphere to have less velocity due to conservation of momentum, which kind of hampers with its ability to complete the actual rules of the game. So as we can see here, the ball's still going, but because of the restitution change, now they both have velocities going to the right, and now it has a much slower velocity. We're going to see it's not going to be able to really get into the green pit this time. So now we've kind of shown what changing restitution values do. So while I correct the restitution values back to their normal states, Shreya is going to talk about our specific model.
Okay, so like Arjan mentioned, we have a great setup here of two balls of the same shape and size, but different masses. We have our first white ball that has a lighter mass and our second yellow ball with a heavier mass. We can control that thruster force on the first white sphere to be able to manipulate the movement of the second. And we've also ensured elastic conditions by modifying their restitution values. So we're going to use this setup and our understanding of conservation of momentum to help us in a real life situation. So we are going to pretend that we have gone to an amusement park for the evening. We've used a sunset background to help us visualize this situation. And we are going to pretend that some of our friends have gotten stuck in a malfunctioning roller coaster cart, and the amusement park has given us control of another lighter cart to be able to push the stuck car back into the cargo bay. So we are going to model this first white sphere as our lighter cart that we get full control over. We're going to model this yellow sphere as that heavier cart that has the same shape but is heavier because it has people in it. And then we're going to model this green spot that we're trying to land into as our cargo bay that we are trying to get our stuck car into so we can save our friends. So we are going to assume that, again, our carts are these spheres. We're going to assume no air resistance, and we still have this friction coefficient of 0.5. So our system here is going to be both of these carts, and we do have some limitations. We are obviously ignoring air resistance, which would be present in this real life situation and would probably affect the car path of the yellow sphere. We're also simplifying these really complex shapes of roller coaster carts down to these spheres. And these carts would probably not have a perfect restitution value of 1, but we have modified that to ensure elastic conditions. So we're going to go ahead and run this simulation, and Arjan is going to kind of walk you through the momentum values to see if we have achieved our goal.
Yep, so we're just going to kind of go through the simulation once again. This time we're paying special attention to the momentum values to see if there's conservation of momentum. So we kind of have our model going so far. We see there's a momentum of about 80, 79-ish right before the collision. I'm going to hit play again, and we're going to see what it is right after the collision. So we're right after the collision. We have like 98. Let me turn on components because it seemed to have gone in the air a bit. You see 98 and about 26. So you see the momentum kind of stays conserved. It's still around the same value. It's not too different. There is a small difference, but that's mostly probably due to the friction value of 0.5 that's kind of detracting from some of the speed that the two spheres are able to gather. So we'll see that that's pretty close conservation of momentum, which is due to our high elasticity value due to that high restitution value. So yeah, that's that model, and then throw it back to Shreya to talk about a different model.
Okay, so we kind of explored two carts with the same sizes and same shapes, but we wanted to dive a little bit deeper with conservation momentum and see how those momentum values would be changed if we maybe use different sizes of shapes and positions of our objects. So in this simulation, we're going to pretend that our second cart is much bigger, has a different shape, and is positioned at the very end of the track. and we're going to see how this behaves.
Okay, so basically the same principles here. We're going to use a different key to actually ignite this specific ball. Obviously, they have different keys because we don't want to make both of the balls go at the same time. So we're using J this time. As you can see, the ball starts going. And then right before the collision, we're going to pause it again. You can kind of see we're starting off with a momentum of about 85, 86. Then the question becomes what happens when they initially collide. So I'm going to let it collide very briefly, and then Shreya can talk about what this interaction, what's happening in the interaction, and what does that mean for momentum. So as you can see, we just let it go a bit. I'll actually go back one to make sure that we can kind of see what the momentums are. It's pretty big. So we have 216, 50, and 24.23. When I actually go to show components, I'll see it's still about 140-ish overall, which is very different momentum than the initial one that we started with. And Shreya can now talk about kind of why that's happening, given the difference of the situation with the size and the location of this ball.
Yeah, so we have this big discrepancy in momentum values, and we can see that in this simulation, instead of the ball traveling on the track horizontally and being hit exactly in the center, we have a bigger ball that was actually launched upwards right when it was hit. So here we are dealing with an external force on this system, which is gravity, and that downwards acceleration is clearly affecting this momentum value post collision. So we do not have perfect conservation of momentum here. So overall, we have observed two simulations that have helped us with this roller coaster situation. We can clearly see conservation of momentum when we have certain sizes and positions with our modeling. And so we learned a lot about conservation of momentum from this setup, and Nick is going to kind of wrap up what we've done.
So yeah, just to restate, our initial goal for the simulation was to demonstrate conservation of momentum, elasticity, and energy, and how in different situations these things can differ. So we used a roller coaster model, as Ray described, and we simplified it to being balls to demonstrate this. So in our first scene, we used restitution. We changed it around to see how that would affect the collision, and we could see that basically as we change the restitution, we could see how momentum would be conserved or not be conserved based on the elasticity. And we use the second scene to show that, size and shape also matters. So when we did the collision there, the introduction of gravity there affected us so that momentum would be conserved there. So overall, I would say that we did show that our concepts, go through this simulation. And we could say that concepts that we learned in physics lab through like the collision lab are reflected in our simulation, so we can apply physics concepts into real life. So Arjan, do you want to talk about your experience, using Algodoo, the program?
Yeah, I will say that, the program overall, it was a very enjoyable experience. It was a lot of fun to use, specifically with this model. I had a lot of fun, just playing around with this collision, and spent a lot of time when I first finished designing this game with getting the ball to land in the green. It's not as easy as I think I made it look in the simulation. I thought I did very good, or this demonstration. But what I will say is that there were a couple problems with using this program in general. I think while it is pretty user-friendly, there are some components that we personally could have wished that the program would show. Like, although it shows velocities, it would have been nice to also show kinetic energy. That way it wouldn't have to be calculated, so we can truly determine if the collision was elastic. Not to say, and also I guess there were some small technical difficulties here and there with specifically creating the perfect track that we wanted. This is what we ended up with. But overall, I'd say Algodoo was a very fun program to use. I think all of us had a great time learning about collisions and conservation of momentum, and really enjoyed the ability to apply some of these concepts we're learning in our class in a new and creative way. So thank you for joining us.